we're going to give you a review on solving log functions. So first, just because it's a review at this point, we wanted to talk about general strategy. So remember, a log equation that you're solving is going to have some log with some base in the equation and contain some expression with x inside of it. And your goal, similar to exponential functions when you see this, is going to be to want to first isolate that log function that contains your variable. So our first strategic approach is identify the log and try to isolate it. And then we kind of looked at two different sets of things that happened, that sometimes when you were able to isolate that log, it was equivalent to some other logarithm on the other side. If those two things had the same base, it would be like saying log base 2 of what equals log base 2 of 5. This would have to be a 5 for them to be equal. So in this case, we're just going to set things equal. We're going to take those values inside that logarithm and they can be set equal. We didn't cancel out the log or anything like that. We just used logic that that's the only way they could be equivalent, and then we could solve that simpler equation. That's one option. The other option might be that once you isolate the logarithm, you might not be able to write something in the same log format on the other side. You might just have a number, and it might be simpler at that point, instead of trying to look for two similar logarithms, to rewrite the equation in a way that you can isolate x. And with all these parts, that you have a base and an exponent and a value of a power, it makes sense that you would rewrite it in exponential form, especially since that is the inverse of the logarithmic form. So that's what we would do. So in this case, we'd have our base of b. Remember, this answer, I like to call it, to the logarithm problem is the exponent. And then you have the value of your power, and you can solve for x from there. So we're going to look at a couple different ways that this plays out. So first, in example 1, you'll notice this would be the case that if I recognize this as a logarithm containing x, it's already isolated, and what it's equal on the other side is a logarithm with the same base. So I essentially can say that 3x plus 9 must equal x plus 10. That's the only way these two logarithms would be equal to each other. And so I'm going to finish solving this. And I get that x is equal to 1/2. Now you do want to make yourself a note on these log functions that we didn't necessarily say on your exponential functions, which is to check, because remember, a logarithm function has a restricted domain. What I mean by that is that trying to calculate the logarithm of 0 or a negative number are undefined in the world of logarithms, which means we really need to make sure that the solution that we get, if we plug it back into the original function, doesn't create an undefined situation where it's trying to take the log of a negative or a 0. So the 1/2 looks good. It doesn't seem to create those situations. All right, so we're going to look at this problem next, example 2. Notice I see the logarithm here. It's a log base 3. It contains the variable inside of it. And then my job is to isolate that. So the first thing I'm going to do is add 3 to both sides. And then I'm going to divide by -2. So now that I've got my log isolated and I don't have whatever's on this side written in a log form that's comparable, I'm looking to rewrite. So it's a base of 3. An exponent of -2 would equal 4x minus 1. So if I'm going to continue solving this, it's important that I understand that 3 to the -2 power is 1/9. And then if I add 1 to both sides, you might want to think of 1 as 9/9. I would get 10/9 equals 4x. And I want to divide by 4 or multiply by 1/4 to isolate x. So I would get that x is equal to, I'm going to simplify a little bit here, 5/18. And then I'm going to make sure that doesn't make anything in my logarithm that's undefined. So I would have 20 over 18 minus 1 inside my logarithm. 20 over 18 is more than 1, so that won't end up being negative or 0, so that should be a good solution. All right, lastly, we're going to look at a logarithm equation that requires you to use properties. So notice here I see a log, and I see another one, and I can't isolate those because I also have a 2. So here's where you have to think about your log properties and ask yourself, can I combine the two logarithms into one? So what we're seeing here is the quotient property, that these two logarithms separated by subtraction is the same as having one single logarithmic function where those expressions inside the logarithm were being divided. So knowing that property well helps me rewrite this. Now, another thing to recognize, this is our common log. We don't have a base written here, but it's a base of 10. So at this point, I'm going to rewrite it in exponential form. So it would say 10 to the second power equals 2x minus 1 over x plus 7. So that's 100 equals 2x minus 1 over x plus 7. And now I'm going to solve for x. So for me here, I need to get x out of the denominator. I'm going to multiply both sides by x plus 7. And that now looks like 100x plus 700 equals 2x minus 1. Now I'm going to gather like terms on one side of the equation and constants on another side of the equation. So I'll have 98x equals negative 701, and I'll be dividing that by 98. So I get that x is equal to negative 701 over 98. And then remember, before you commit to that answer, since this was a log equation, we really want to check. If you look at what's inside of that first logarithm, it's 2x minus 1. If I multiply this stuff together, notice this will definitely be a negative value. I'd have log of a negative value in my problem, and that's going to cause something that's undefined, so it's not going to work. So this solution doesn't actually work, it's extraneous, and because I have no other solutions that I came up with, then this problem has no solution.